Welcome to Excellent Grades Academy. This is Dr. Byson EM. Today we're looking at organic chemistry. And under organic chemistry, we're looking at alkyl halides. Let's get into this video. Okay. So, question is, what are alkyl halides? So, what are alkyl halides? Alkyl halides. Okay. So, these are organic compounds that contain an alkane. So it's an alkane with one hydrogen replaced by a halogen. Okay. So a halogen is simply a group 7 element. So these are group 7 elements. Those are halogens. And what you should know about halogens is that they have a very high electronegativity, meaning that their ability to draw electrons to themselves are very high on the periodic table. So for example, if I have this alkane here, this is butane. Okay. If I replace one hydrogen here with a halogen, it will change from an alkane into an alkyl halide. So it will be this. Say I attach fluorine here. So this is what we call an alkyl halide. Okay. All right. Now, alkyl halides are classified as primary alkyl halide. So classification of alkyl halides. Alkyl halides are classified as number 1, methyl halides. So this is an alkyl halide where you have a halogen that is attached to one carbon. Okay, so for example, the halogen is attached to one carbon there. This is what we call a methyl halide. And then when you have a halogen attached to a primary carbon, so this carbon here, this is a primary carbon. Why? Because this carbon here is attached to only one carbon here, which is here. So because the halogen is attached to a primary carbon, this is what we call a primary halide. So this is a primary halide. It is denoted as 1 degrees, primary halide. But then when we have a halogen attached to a secondary carbon, like in this case here, this is a secondary halide. So this is a secondary halide. Why? Because the halogen is attached to a secondary carbon. Then last but not the least, we have got what we call a tertiary halide. So a tertiary halide, the halogen here is attached to this carbon here. This carbon here is a tertiary carbon. Why? Because this carbon here is attached to 1, 2, 3 carbons. So this is a tertiary halide, which is 3 degrees. So those are the classifications of alkyl halides. Okay, those are the classifications of alkyl halide. Now let's look at the chemistry of alkyl halides. So the chemistry will give us an idea of why alkyl halides undergo certain reactions. So chemistry of alkyl halides. This is a very important concept to know. All right. So if this is my alkyl halide here, and then this is attached to a halogen, like this. All right. Now, this carbon here that is attached to a halogen is what we call the alpha carbon. So this is the alpha carbon. Alpha carbon, it is noted like that. Okay. So the carbon that is attached directly to a halogen is the alpha carbon. Okay. And then the bond that is formed between the alpha carbon and the halogen, this is a polar covalent bond. Polar covalent bond. So there is sharing of electrons between the carbon and the halogen. But what you need to understand is that the halogen has got a stronger pool of these electrons that are being shared with the alpha carbon. So the electrons are going to be closer to the halogen than the carbon. So the halogen will be partially negative, whilst the alpha carbon will be partially positive. That is why this covalent bond between the alpha carbon and the halogen is polar, because there is charge distribution due to significant electronegativity difference between the halogen and the carbon. All right. So now, because the alpha carbon here is positively charged, if it is placed in a solution which has got negatively charged species, or species that have got a lone pair of electrons, they will be attracted to the positive charge. Why? Because we know that negative charges are attracted to positive charges. Opposite charges attract. Okay, so this positive center here, which is the alpha carbon, is going to attract species that are negatively charged and that have got a lone pair of electrons. Because this center here, the alpha carbon, is positively charged, it is referred to as an electrophilic center. So this is an electrophile. So it is an electrophile. An electrophile, by definition, so let's write it this side, electrophile. So an electrophile, this is a species or compound, that attracts, so it attracts negatively charged, negatively charged compounds or Lewis bases. So Lewis bases. Lewis bases are simply compounds that have got a lone pair of electrons. Lone pair of electrons. Now, when we talk about lone pair of electrons, we're talking about pairs of electrons that are non-bonded. For example, if you have oxygen here and it has 2 electrons like this, this is a lone pair of electrons. Okay. So now the electrophilic center, which is the electrophile, in this case, which is the alpha carbon, always attracts negatively charged species or Lewis bases, which are just compounds that have got the lone pair of electrons. Okay. So always remember, on an alkyl halide, the alpha carbon is positively charged and it will attract Lewis bases or negatively charged species. The negatively charged species or the Lewis bases that will come and attract or will come and act on the alpha carbon are what we call nucleophiles. Okay. So these are nucleophiles. Okay. Nucleophiles. So those are nucleophiles. So nucleophiles are the ones that will come and be attracted at the alpha carbon. All right. Now, when you look at this carbon here, that is attached directly to the alpha carbon, this carbon here is what we call the beta carbon. So this is the beta carbon. One interesting fact about the beta carbon is that these hydrogens that are attached to our beta carbon are known as beta hydrogens. So these are beta hydrogens. And the beta hydrogens are acidic. They are acidic meaning that they can easily be lost, they can easily be given away. Remember, an acid is a proton donor, and the proton that it gives away is a hydrogen. So these are acidic. The beta hydrogens are acidic. So if you have a base in solution, the base will come and get this acidic hydrogen here. That is the basis for how some reactions under alkyl halides occur, and those reactions we're going to look at them. All right, so this is the chemistry of an alkyl halide. And from this chemistry, if you understand it, you find that all the reactions that we're going to conduct under alkyl halides are going to be very simple to you. Okay, so now under the alkyl halide, so if this is our alkyl halide here, okay, and then you have attached a halogen. This alkyl halide is what we call a substrate. So the alkyl halide is a substrate. Why? Because this is a species that is going to undergo a chemical reaction. Okay, it's going to undergo a chemical reaction. All right, now let's look at the type of chemical reactions that alkyl halides undergo. So reactions of alkyl halides. Alkyl halides undergo two types of chemical reactions. So alkyl halides undergo two types of chemical reactions. These include, number one, substitution reactions. Substitution reactions. Number two is elimination reactions. Elimination reactions. So once we do these two types of reactions, then we'll be done with alkyl halides. All right, so let's delve into substitution reactions and look at what they are and the types of substitution reactions. So substitution reactions. Substitution reactions. What are they? What do they involve? So these are chemical reactions. So chemical reactions where the halogen, so the halogen is called the leaving group. Okay. The halogen, the leaving group on the alkyl halide. So remember, we said the alkyl halide is called the substrate because it is a species that is undergoing a chemical reaction. Substrate is replaced. So is replaced by a nucleophile. So those are substitution reactions. So these are chemical reactions where the halogen, which is the leaving group on the alkyl halide, therein called the substrate, is replaced by a nucleophile. Remember, we said that a nucleophile is a negatively charged species or a species that has got a lone pair of electrons referred to as a Lewis base. There are two types of substitution reactions. So they are two types of substitution reactions. Substitution reactions. Namely, one, substitution nucleophilic. So nucleophilic reactions by second order. So second order kinetics. These are denoted as SN2. And then the second type of reactions are called substitution. So substitution nucleophilic reactions by first order kinetics. These are denoted as SN1. Okay. let's delve into substitution nucleophilic reactions by second order and see how they react. Okay, so let's look at SN2 reactions. SN2 reactions. So SN2 reactions, these are reactions that, these occur in one step. So they occur in one step. Number two, there is formation of a transition state. So you always have to know there's the formation of transition state. Number three, the nucleophile. So the nucleophile participates in the rate determining state. So the rate of an SN2 reaction is dependent both on the rate is simply the speed of an SN2 reaction depends on both the substrate, which is the alkyl halide, and the nucleophile. So the rate law for an SN2 reaction is like this. Rate is equals to the reaction constant K times the concentration of the alkyl halide times the concentration of the nucleophile. So you've seen that the rate of an SN2 reaction depends both on the alkyl halide and the nucleophile. So this is very important to know, because sometimes they will tell you if we increase the concentration of the nucleophile, we double it, what will be the effect on the rate of an SN2 reaction? So if you double the nucleophile, the rate of an SN2 reaction will also double. All right. If you double the concentration of the alkyl halide, the rate of an SN2 reaction will also double. If you double the concentration of both the alkyl halide and the nucleophile, the rate of an SN2 reaction will be 4 times, because this will be 2 here, this will be 2. 2 times 2, it will be 4. So we say that the rate goes up by 4 times, or we say the rate quadruples. Okay, let's continue. SN2 reactions are favored. So they are favored by polar aprotic solvents. So polar aprotic solvents, let's just define them. Let me use a different color here. So polar aprotic solvents are solvents which do not form hydrogen bonds. So examples of polar aprotic solvents which you need to know. Number 1 is acetone, most commonly used. And then you've got tetrahydrofuran, which is denoted as THF. And then we have dimethyl sulfoxide. Dimethyl sulfoxide is denoted as DMSO. So these are polar aprotic solvents, and these are the solvents which favor SN2 reactions. You need to know this. So whenever you see a solvent like this, just know that an SN2 reaction is taking place. All right. And then SN2 reactions occur very fast in primary alkyl halide as compared to secondary alkyl halides. and they occur very slowly, or they don't even occur in tertiary alkyl halides. All right, so now let's look at examples of how the mechanism of these SN2 reactions occur. Okay, examples. Okay, so what product would form from an SN2 reaction of the following? So what product of an SN2 reaction would form? So would form if you react 1-bromo 2-methyl. So if you react 2-bromo-butane rather with an, so this is our butane, and then you put this in hydroxide ion there. So this is A. So what is going to happen here? See, this here is our alpha carbon, and we said that the alpha carbon is partially positive. This partial positive is going to attract this negatively charged nucleophile. So this nucleophile is going to attack the alpha carbon from the backside of the halogen. So there's going to be 180 backside nucleophilic attack. So this nucleophile will attack 180 degrees at the back of the halogen. When it does that, so let's just write here, backside nucleophilic attack. Nucleophilic attack. Okay. So the nucleophile attacks 180 degrees at the back of the halogen. And then this halogen, the bond between the halogen and the alpha carbon is going to break. And the halogen is going to get these bonds. Okay. So the product that is going to be formed is going to be this. Plus this halogen here left, but it left with electrons, so it's negatively charged. So as you can see from here, the halogen on the alkyl halide was replaced by the nucleophile. How? Because the nucleophile attacked the alpha carbon, which is partially positive, from the back of the leaving group, which was the halogen. So this is how an SN2 reaction takes place. Okay, so now let's look at this example where we use a stereoisomer. So this wasn't an isomer. I'm using a stereoisomer now. So this stereoisomer is simply ara 2-bromobutane. Okay, why is it ara? Because the alpha carbon here, when you assign the Can ingot prelog system or the ara and S configuration, you find that the bromine here will be number 1 priority, followed by this chain, followed by this chain. So the rotation will be clockwise. That's why this is ara. Okay, so it is the same mechanism that is going to take place. The nucleophile is coming and it will attack at the alpha carbon 180 degrees at the back of the leaving group. Then this leaving group goes. When that leaving group goes, what is going to form is this product here. Plus, now if you notice, the nucleophile, I've used dashes here, not a wedge, signifying that, showing that the nucleophile joined at the back. Why? Because it went and attacked at the back of the leaving group. This leaving group here was in front. So when the nucleophile came, it went and attacked from the back. That's why it joined at the back here. Whenever you are doing an SN2 reaction, always remember this. If your substrate, the alkyl halide that is reacting, is an ara configuration, the product that is going to form is going to be an S configuration product. So this product here is simply S2-butanol. So an S configuration is formed from an R configuration. If you start with an S configuration, if that S configuration alkyl halide undergoes an SN2 reaction, what is going to form is an R configuration product. Okay, let's look at another example. So this example is very easy. They're just saying assign the following alkyl halides. Alkyl halides classifications. So just classify the following alkyl halides. So the first alkyl halide, let me use this, is this one here. And then the second one, third one, okay. So what is the classification of this alkyl halide? So this first one is a tertiary alkyl halide. Why? Because the alpha carbon here, where the halogen is attached to 3 carbons. 1, 2, 3. So this is tertiary. This one here is a secondary alkyl halide. Why? Because the alpha carbon is attached to 2 carbons. This one here is the primary alkyl halide, meaning that the alpha carbon here is only attached to 1 other carbon. All right. So now, if they ask you which one here is going to be faster when it reacts by an SN2 reaction, the one that is going to be faster is 3. Why? Because 3 is a primary alkyl halide, followed by 2. Why? Because 2 is a primary alkyl halide, and the slowest will be the first one here, because this is a tertiary alkyl halide. So always remember this. Alkyl halides, if they undergo an SN2 reaction, the more substituted it is, the slower it is. Okay, so tertiary here is more substituted. Let's look at the last example. So D. So what is the reaction that is going to take place from this? So you have a primary alkyl halide there reacting in ethoxide. All right, in ethoxide there, and say I put DMSO here. So DMSO here is a polar aprotic solvent. So we know this is going to occur by SN2 reaction. The mechanism that is going to take place, if I say this occurs by SN2, is that the nucleophile is going to attack the alpha carbon from behind the leaving group, and then the leaving group is going to leave. When that happens, then the product that is going to form is this. The oxygen here plus the bromine that left. Okay, so we started with 1, 2, 3, 4, 5. We started with 1 bromopentane here. 1 bromopentane. And then the product that we formed here is an ether, because this carbon chain here, which is an ethane, is bonded to this pentane by an oxygen. So this ether is simply ethyl pentyl ether, meaning that the ethyl and the pentyl chains are connected by an oxygen. Ether simply means oxygen. Okay. Ether simply means oxygen. E. If you have this alkyl halide there, and then you react it with a cyanide ion, how is the reaction going to take place? Okay, say there is THF here as a solvent. So this nucleophile will come and attack from the backside, and then this leaving group is going to go. So the product that you are going to form is this. The leaving group there will be replaced by this nucleophile, and the chloride will be in solution, negatively charged, because it took the electrons with it there. All right, so that is how SN2 reactions take place. Let's look at one last example before we end this video. So if you have this compound here, and then you react this compound by a methoxide, okay, and this methoxide is placed in acetone, say acetone, and I tell you this is occurring by SN2 reactions. So this, let me use another color, this will come, attack from behind, this leaves. What you're going to have is this product here. All right, so now you have an ether that is formed from this reaction. So always know SN2 reactions occur with simple nucleophiles, and not bulky nucleophiles. So bulky, not bulky nucleophiles. And the nucleophiles should be strong nucleophiles. Okay. So they will occur with simple nucleophiles and not bulky nucleophiles. For example, this is a simple nucleophile here, hydroxide. So this is a simple nucleophile. But if you get state butoxide, this is state butoxide. This is a bulky nucleophile. Okay, this is bulky. Why? Because look at all these carbon chains that are attached. So this is carbon here, there's a methyl group here, there's a methyl group here, there's a methyl group here. So this is a big nucleophile. So you don't expect SN2 reactions to occur with this nucleophile. Why? Because for this nucleophile to come and attack the alpha carbon, it has a lot of surrounding groups. So there's going to be a lot of hindrance. So this provides what we call steric hindrance. So whenever you see a bulky nucleophile, just know that an SN2 reaction will not occur there. One other thing you should know is that negatively charged nucleophiles are, so negatively charged nucleophiles are stronger. So they're stronger than neutral nucleophiles. Neutral nucleophiles are just those nucleophiles that have got electron pairs but are not negatively charged. Okay, so for example, if I take water, this is a nucleophile because it has lone pairs of electrons, and I take hydroxide. Between these two, hydroxide is stronger. Why? Because hydroxide has got a negative charge there than water. Okay. Or if I take ammonia here, it has a lone pair of electrons there, so it's a nucleophile. And I take amine. Okay, the amine has got a negative charge there. So this one here is stronger because it has a negative charge. So when you compare neutral nucleophiles and negatively charged nucleophiles, the ones that have got a negative charge are stronger, and hence the SN2 reactions will occur more readily in nucleophiles that are negatively charged, because SN2 reactions depend on the nucleophile. All right, so in our next video, we're going to look at SN1 reactions, the conditions that favor SN1 reactions, and the reaction rates of SN1 reactions, and the reaction mechanisms. See you in the next video.